This is part 2 of chapter 8, 8.4, bond polarity and electronegativity, which we'll touch again in chapter 9 in terms of determining if the molecule is polar or nonpolar. But here we have ionic compounds and covalent compounds. And we have three categories. We say ionic character, we have polar covalent, sharing the electrons, but there's a polarity difference between the H and the Cl, and we have nonpolar. Here we see two of the same elements, and we'll talk in a little bit more detail in terms of the values between the electronegativity differences. So we can have extremes, like I just said, the ionic, metal and nonmetal. We have the nonpolar covalent, and in between these two extremes we have this polar covalent. Electronegativity is a characteristic when you have a bond, how much the electrons in a bond gets pulled towards one element versus the other. These are relative values, and this will be given to you on exam, these values. For instance, fluorine is the most electronegative element, 4.0, and the least electronegative here, cesium, 0.7. There are no units for electronegativity, and the general trend is the electronegativity increases as you go from left to right and down or bottom up. So if you just keep in mind that the bottom left is not very electronegative and the fluorine is the most electronegative, you can develop the trend. So the scale we use, based on, as I just said, we compare two elements in the bond and see its electronegativity difference. If we measure the difference, for instance here, between the nitrogen and the hydrogen in NH3, so we measure the electronegativity difference. Again, these two values, 3 and 2.1, will be given to you. We get a value of 0.9. And according to this table, we have a classification whereby if the value between the two elements is between 0 and 0.4, we say it's non-polar covalent. If it's between 0.4 and 1.9, we say polar covalent. And anything greater than 1.9, we say ionic. So in this case, 0.9, the electronegativity difference is 0.9. So we say it's polar covalent bond. The same table I just showed you in the previous slide. Let's take a look at an example here. If we have cesium chloride, if we did the math, again, the electronegativity difference will be given to you. 3 minus 0.7 is 2.3 is ionic. But you could even determine this is ionic bond before even doing the calculation, because you know cesium is a metal, chlorine is a nonmetal. So when you have a metal and a nonmetal, that should click for you that it's an ionic compound. Let's take a look at water, H2O. If we compare the hydrogen and the oxygen, electronegativity difference is 1.4, and we associate that with a polar covalent bond. And the third example, the N and the N in this H2N and H2, we want to compare this bond or compare these two elements. They're the same, so their electronegativity difference will be 0, and we get a covalent bond. We can say nonpolar covalent. So we'll just give you a try. Which two atoms will form a polar covalent compound? So that's when you have a value between 0.4 and 1.8. We look at the first one, sodium and fluorine. Sodium 0.9, fluorine 4.0. That's a difference of 3.1. So right away, that should tell you that's an ionic compound. For when you have two elements that are the same, that's a non-polar covalent. We look here between the sodium and the oxygen. The sodium is 0.9. The oxygen is 3.5. So 3.5 minus 0.9, 2.6. Again, that's ionic. So we look at the third one. By elimination, H and Br, which is hydrogen 2.1, bromine is 2.8. Difference is 0.7. So that will be our polar covalent compound. So when we have a polar covalent bond, we create something called a dipole. Di means two. Pole, in this case, we have a positive end and a negative end. We can represent this with a partial negative charge, which means in a bond, let's look at water, for instance, we know that in water, the oxygen is more electronegative. So in this particular covalent bond, the electrons will spend more time around the oxygen. Therefore, we designate a partial negative charge, and as a result, the hydrogen will be more of a partial positive charge. So this is one way to write it. We have partial negative and partial positive. You can also write it on the left here. We see that the hydrogen, the vector shows that towards the oxygen. So if we add these two vectors up, we don't have to go into too much detail. We have a charge, a negative charge going towards the oxygen in the upward direction. So again, these two ways to represent a dipole. Again, the same example, we have a vector here for HF. We said F is the most electronegative element, 4.0. So the vector goes towards the fluorine, and we can write a partial positive charge or a partial negative charge. And this is just an image here that shows that the electrons spend more time around the fluorine, giving it a partial negative charge. Again, this photo here shows the nonpolar covalent equal distribution of electrons versus a covalent polar between 0.4 and 1.8. So we have more electrons spent around the element here on the right side. And ionic bond is a complete transfer of an electron here from the cation, you can say, to the anion. So just a review about Lewis structures. We said the first step is to find the total valence electrons. So you need the periodic table for this to figure out how many valence electrons are on the outside. Once we have the total valence electrons, step 2 is choose the central atom if there's 3 or more elements. The one that needs the most valence electrons to make 8 will be in the middle. And we connect, step 3, we connect the elements with a line to show a covalent bond. Again, we focus on covalent bonds. We place any of the remaining electrons on the non-central atom on the outside. And there's a possibility of forming triple bonds or double bonds as well, if needed, to satisfy octet rules and to satisfy the total valence electrons used. So as an example, let's draw nitrate. You can pause the video. As you know, nitrate, NO3 minus. So NO3 minus, first step, let's figure out the total valence electrons. From the nitrogen, there's 5. From the oxygen, it's 6. 6 times 3, 18. 18 plus 5 plus the negative charge here, we have 24 valence electrons. Okay, so we want to figure out which one goes in the middle. The nitrogen will go in the middle because it has 5 valence electrons. It needs 3 more to be happy to make 8. The oxygen has 6 valence electrons. It needs 2 more to be happy to make 8. So N will go in the middle. Let's connect the oxygens. The oxygen can be above or below, it's okay. we want to use up our 24 valence electrons. We first have to say there's a negative charge. So if we use up our 24, 1, 2, 3, 4, 5, 6, 7, 8 in the bond between the nitrogen and the oxygen on the left, 9, 10, we go below, 11, 12, 13, 14, 15, 16, and on the right, 17, 18, 19, 20, 21, 22, 23, 24. So we used up our 24 valence electrons. Does each one have 8? The oxygen, yes, each oxygen has 8. However, the nitrogen only has 6. So what we're going to do is remove 2 of the electrons. Let's remove the 2 on the right. And let's create a double bond. So now we still have 24 valence electrons, and now the nitrogen has 8 around for the central atom. We can also draw like this, where the nitrogen is in the middle, the oxygen is below, gain the negative charge, 1, 2, 3, 4, 5, 6, start on the right, 8 with a bond, 9, 10, 11, 12 going below, 13, 14, 15, 16 on the left, 17, 18, 19, 20, 21, 22, 23, 24. And we can finish this off with the double bond being on the left side. Okay, negative charge, 2, 3, 4. I'll just draw all the electrons. And we'll talk in the next slide, but yes, these 3 structures are valid for Lewis structures. The only difference between the 3 is the movement of the electrons in the double bond. So we call that resonance, and a resonance structure is any 2 or more possible structures of the same compound that have identical geometry but different arrangement of electrons. So all we're doing is moving the electrons around. Everything still satisfies our Lewis structure rules. We still use the total valence electron count, and each one should have 8 electrons. So this is ozone. The total valence electrons here is 18. So both cases are valid, where we have the double bond on the right side, we have the double bond on the left side on the structure on our left, and the only difference is the double bond has moved. The electrons have moved from one side to the other. If I had a jar of O3, the actual structure would be something in between, an average. Right now, these 2 structures show the extreme cases of how it would appear in a beaker. So to designate a resonance, we use this double arrow. So in this case, we would have a double arrow to show the back and forth between the 2 structures. So let's give it a try with carbonate. You can pause the video. We're going to draw the acceptable Lewis structures. So for CO3, 2-, again, there's 4 from the carbon, 18 from the oxygens, 6 times 3, and another 2 electrons. So that gives us a total of 24 valence electrons. We place the carbon in the middle. It needs 4 more to make 8. And we have the oxygens around the carbon, and we use up our 24 valence electrons. 1, 2, I'm starting on the left, 3, 4, 5, 6, 7, 8, we'll go above, 9, 10, 11, 12, 13, 14, 15, 16, and go to the right, 17, 18, 19, 20, 21, 22. And the same thing with nitrate. We're going to add a double bond here to use up our 23 and 24 so that the carbon gets 8 valence electrons. We need to indicate that it is a 2- charge. And if we want to write the resonance structures, meaning the double bonds have moved, the carbon will draw the double bond with the oxygen above. And all these structures has 24 valence electrons. Each one has 8. And we can draw one more resonance structure. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with the bonds 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this is the correct Lewis structure. It says draw all acceptable, so these are all valid. They're in resonance. If you wanted to, sometimes you'll see in a textbook, you'll have this O, O, and an O, and you can actually draw some dots here to show that the double bonds have been moving from one to the other. Draw all acceptable Lewis structures of dinitrogen monoxide. So again, we find the total valence electrons is 16, 10 from the nitrogens and 6 from the oxygens. Nitrogen will go in the middle. So let's start with a double bond. Let's see if we can do this. 1, 2, 3, 4. In the double bond is 8 on the left. The double bond on the right is 12, 13, 14, 15, 16. Can we draw other structures? Yes, just like carbon dioxide, we can draw a resonance structure where we have a triple bond on the left and a single bond on the right. You can draw another one, another resonance structure where we have the triple bond on the right. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, 11, 12, 13, 14, and on the oxygen, the lone pair, 15, 16. If we were to draw the asked which was the best structure, you would use your formal charges. And we can see here the N on the left. I'll do this quickly for you. The formal charge, the structure on the left would be 5 minus 2 minus 4 is -1. In the middle would be +1. And on the right side for the oxygen would be 6 minus 2 minus 4 is 0. The structure in the middle, it would be 5 minus 3 minus 0 would be +2. In the middle, it would be 5 minus 4 plus 1. And on the right, it would be 6 minus 1 minus 6, which is -1. For the structure on the right, it would be 5 minus 1 minus 6, so that would be -2. In the middle, it would be nitrogen, it would be 5 minus 4 is +1. And on the right, it would be 6 minus 3 minus 2 plus 1. So the one with the least amount of formal charges would be the structure on the left. That would be the most likely structure. We also can extend the structure of resonance to hydrocarbons, hydrogen and carbons. You'll see this much more in organic chemistry. Benzene here is designated as C6H6. which has 6 carbons and 6 hydrogens. These are considered resonance, as you notice here, the double bonds, we can say at the top, in the bottom left corner, and the bottom right corner. And what actually happens here is the double bond, the electrons and double bond slide over. The electrons from this double bond slide over. And the electrons from this double bond slide over, pointing with an arrow where the electrons go, and we get this other structure here. So these two are in resonance. Resonance creates stability. We have a double bond. Each structure has 3 double bonds, and each carbon has 1 hydrogen attached. So if you look at both cases, there's still 8 electrons for each carbon. The octet rule, and each hydrogen has 2 electrons. This is a skeletal way of drawing, which we'll again talk more in organic chemistry, where you just show the carbons. The hydrogens are not noted here. And if we want to write a more abbreviated version of this resonance structure, we have here again our 6-membered ring, and we draw a big circle in the middle to show the resonance structures. So experimentally, the lengths between the carbons are the same. This is shown in theory based on the resonance structures. So again, these two are extremes, and you have something in the middle. So as I said at the beginning, the majority follow the octet rule. There are some exceptions, of course. Electron deficient octets, meaning are compounds or elements in a compound that have less than 8, and there are expanded octets where they have more than 8. Let's just talk about a few. The electron deficient octets, where an element has less than 8. Most common ones are with boron as a central atom, beryllium, also I should add aluminum as well. So we have an example of a compound that has less than 8 electrons on the central atom, BF3, boron trifluoride. This structure here is more preferred than the structure on the right. These have more of a length towards single bonds. The structure on the right has 3 resonance structures. However, if you look at the formal charges, the formal charge on the boron here is, for the boron, is 3 minus 3 minus 0, which gives us a formal charge of 0. If you look at the formal charge on the boron on the right side, one way to explain, it has a 3 minus 4 minus 0, which is negative 1. So the structure on the left is preferred. You can also think of fluorine being the most electronegative element. It wants to pull and take as many electrons as it can as well. So this is one example of a electron deficient octet in the middle. Or I should say the central atom has less than 8 electrons. Here's another example with beryllium chloride. I can quickly draw this. We have the beryllium in the middle. Total valence electrons is 2 from the beryllium and 14 from the chlorine, so 16 altogether. So if I were to draw the electrons on the left, 1 on 2, 3, 4, 5, 6 on the bond, 7, 8 on the bond on the right, 9, 10, 11, 12, 13, 14, 15, 16, and the formal charge on each one of these elements is 0, 0, and 0. We have the expanded octet. Those occur in the periodic table where the third period, so between 3A and 7A. It also occurs in the transition metals. We'll focus on main group elements on the third period, 3A to 7A, and below the 4th, 5th rows, etc. And so, for instance, the row of carbon, nitrogen, oxygen, and fluorine, these cannot accept more than 8 electrons because they don't have any d orbitals that are readily available. Meaning if you look at the elements before, so if you have a periodic table here, I'm going to draw. These elements below the carbon, nitrogen, oxygen, fluorine, all of these here and the p orbitals can take up more than 8 because there are some empty d electrons orbitals that are not filled. So here are some examples. We have xenon tetrafluoride. The xenon here has more than 8. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And another example here is phosphorus tetrachloride. Phosphorus is located under the nitrogen group. Here the phosphorus has 10 valence electrons on the central atom. So let's pause and try one on our own. The aluminum chloride, AlCl3. So the total valence electrons is 21 from the chlorines, and so from the chlorides, and 3 from the aluminum, so to give us a total of 24 valence electrons. The aluminum goes in the middle. It needs 5 more to make 8, versus the chlorine only needs 1 more to make 8, and we want to use up our 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's go to the right. 13, 14, 15, 16, 17, 18. And then the bonds, 19, 20, 21, 22, 23, 24. So it's 24 valence electrons. The chlorines have 8. The aluminum only has 6. If we did the formal charge on each element, we get formal charges of 0, 0, 0, and 0. For sulfate, so if you guys recall, sulfate is SO4, 2-. So I'll draw the sulfur will go in the middle. The oxygens will go on the left, above, to the right, and below. We want to use up a total valence electron here. It would be 24 from the oxygen, 30 in total with the sulfur, and then 2 more to make 32 valence electrons. So let's start drawing. 1, 2, 3, 4, 5, 6, 7, 8, below 9, 10, 11, 12, 13, 14, 15, 16. Let's go to the right. 17, 18, 19, 20, 21, 22, 23, 24. Let's go above. 25, 26, 27, 28, 29, 30, 31, 32. You might think this is a valid Lewis structure, which it is. We used up our 32 valence electrons. However, if you look at the formal charge on each one of these, it's for the oxygen, 6 minus 1 minus 6 is -1. Each oxygen would be -1, -1, -1. And the sulfur in the middle would be +2. So that's quite a few formal charges. Let's see what happens when we add a double bond instead. So let me remove the formal charges. Like I said, I'm going to remove, let's say, the oxygens from the bottom, 2 of the oxygens, 2 of the electrons from the bottom, 2 of the electrons from the oxygen on the left, and let's make double bonds now. We again have 32 valence electrons. The sulfur has more than 8, but that's allowed. It is in the p orbitals below our second row. So here we have 32 valence electrons, and we're able to find the formal charge. Let's try. On the oxygen on the left, it's 0. On the oxygen below, it's 0. On the sulfur in the middle, it's 0, 6 minus 0. On the right, sorry, on the above, it's -1 and -1. So this has less formal charges than the previous structure where we had all single bonds. So this is preferred. We draw resonance structures. I'm not going to draw the lone pairs, but I'll draw where the double bonds can shift. So we have above, we're going to draw 6 of them. Again, I'm not going to draw the lone pairs, which I should. Again, the charge is -2. We can have the sulfur, the double bond, across from each other. So that's 3 structures. Let's draw another one to the right. The ones on the right and above. To the bottom and to the right. And I'm missing one more. So let's figure this out. It would be the top and the left. So this would be an octet rule where there is more than 8 electrons around the central atom. And that concludes chapter 8.